Labguy here. This is the long-awaited return video that I mentioned in my previous video. Today we're going to look at a project I call the Boboscope. It's just a name. I'll explain it later. So, without further ado, let's get into it, shall we? I'll see you after the deep dive. This project is called the Boboscope, in tribute to the fellow who gave me this nifty little cathode ray tube. Hi, Bob. If you don't know me by now, I give all of my projects a handy name to simplify referring to them in general. The project will be a 1-inch CRT-based unit with power supply and the CRT tube providing the basic facilities of an X, Y, and Z input oscilloscope module on which to build a couple of nifty projects. What I have in mind today is eventually supporting one of my SparkFun o'clock boards and my original tiny TV board. The first to make a classic scope clock and the latter to make a cute tiny monochrome television monitor. These enhancements will be covered in future episodes of the series. This is the D3-130GH 1-inch or 3 centimeter cathode ray tube, made by Brimar of England in January of 1978. This was a recent gift from a friend. Thanks, Bob. You know who you are. Unlike the 1CP1 CRT used in the NBTV CRT televisor, this Brimar tube is not pin-starved. What I mean by that is that this tube has 13 pins, more than enough for every internal electrode to have a dedicated connection to the outside world. In the case of the 1CP1, which has only 8 pins, several electrodes must share a pin. The 1CP1 was made by Cossor in England. The 1CP1 was also known as the DG3-91 and made by Philips in Holland. In the 1CP1, the cathode and the focus electrode G3 share pin 7. This is not a problem for the designer because this arrangement results in what Cossor describes as a self-focusing electron gun. Then we come to deflection electrode D', second anode A2, and fourth anode A4. These all share pin 2. This is a medium-grade problem. It makes the deflection drive to the plates D1 and D1' more complex and limits the tube's use in general-purpose applications. The James Millen oscilloscope module used in the NBTV CRT televisor used the 1CP1 CRT and did cause me some minor headaches in interfacing the scan circuits. The D1 and D1' deflection plate connections do not load the outputs of the deflection amplifier correctly. They cause a slight imbalance that was within the adjustment range of my scan amplifier circuits. In the end, this arrangement was made to work adequately, but I don't consider it to be elegant. Back to the Brimar D3-130GH. This tube has none of the problems mentioned and is very straightforward to apply. Each electrode is available for maximum design flexibility. Let's look at the specs for the tube to see what we will need to get it to light up and give us a beam spot on the face. Active deflection comes later. From the bottom up, we first see that the heater power requires the standard 6.3 volts at a current of 300 milliamps. This is just under 1.9 watts. The next design consideration is the cathode to anode 2 operating voltage. This is shown in the table as VK to A2 being 1000 volts. This is the operating voltage from cathode to the second anode. When designing a CRT electron gun voltage divider, this is the first consideration above all else. All electrode voltages shown here are measured relative to the cathode, electrode K. G1 is the beam intensity control grid. It operates at a negative voltage relative to the cathode, in this case between -20 and -48 volts. The last set of electrodes are the deflection plates, two pairs labeled SX and SY. These are specified as volts per millimeter of deflection, about 100 volts average for the SX and about 75 volts for SY. Why the difference in deflection sensitivity, you might ask? Great question. This is because the plates labeled SX are closer to the screen and SY are farther back. Bending the beam close to the screen requires more voltage because it travels the shorter distance. Bending the beam farther back allows the beam farther to travel and thus a wider sweep per volt. All electrostatically deflected tubes work this way. At first glance, this circuit may appear a bit intimidating to the uninitiated. I covered a very similar circuit in the NBTV CRT televisor deep dive video. We will cover this version again here as it is designed for the Brimar tube, which is not using any pin sharing schemes. Ignore the upper portion of the divider string for now. Let's start at the bottom and work our way up the resistor string so that you can see how the voltages for each tube element are derived. This portion of the circuit powers up the electron gun portion of the tube, generates and focuses the beam onto the phosphor screen, lighting up a spot. This string was designed such that each 1 k ohm of resistance has a voltage drop of 1 volt. The current flowing in the string is thus 1 milliamp. Recalling your Ohm's law, 1 volt divided by 1,000 ohms equals 1,000th of an amp, or 1 milliamp. This relationship was chosen to keep the arithmetic as simple as possible. Take note of the voltages indicated to the left of the resistor string. Allow me to explain the nomenclature I used. There are two voltages indicated. The upper voltage is the DC voltage measured at that point relative to the circuit ground. The voltage below it, in parentheses, is the voltage measured relative to the cathode of the tube, element K, sitting between the two pots on the string. In this way, we can see the circuit values as well as the voltages as seen from the perspective of the tube. If that is confusing, don't waste time pondering it. All will become clear as we proceed. Referring to the point labeled K, you can see this is at 0 volts cathode potential as indicated on the data sheet. Looking at the brightness control, RV3, we see it can be set from -20 to -70 volts relative to the cathode K. This is the operating range of the control grid G1. In the same way, the voltage range of the focus control, RV2, is 50 volts to 150 volts relative to the cathode. The center of the control would then provide the 100 volts required by the focus electrode, A3, in the CRT. Easy peasy. Just to mention, resistors R3 and R4 at the top of this image make up the difference between the top of the focus control and the bottom of the spot positioning controls, which we cover next. Moving to the upper portion of the voltage divider, there are several things going on here. First, we need to establish our 1000 volts for the second anode, A2. This is accomplished by resistors R1 and R2. Notice that the 1 milliamp of current coming up the string is divided into two paths at the top of resistor R3. 200 microamps continues up through R1 and R2. The remaining 800 microamps travels to the right towards the centering controls. We will return to that path in a moment. Going up through R2 and R1, we establish the 1000 volts needed by anode 2. This may seem odd at first, but there is a darn good reason for this. The deflection plates must be nominally the same voltage as the second anode to avoid defocusing the electron beam as it passes through this region of the electron gun. Notice on the diagram how the A2 symbol and the centers of the four centering pots are all on the same horizontal line. This visually implies that they are all at the same voltage when both position controls are centered. In that condition, the spot is centered on the face of the tube. Got it? Good. Moving on. Let's look at the centering control circuits next. A word about R8 and R9, the 62K ohm resistors, in series with the top and bottom connections of the position control pots. I originally designed this system to use 1.5 megohm pots, but was unable to purchase any in that same size class as the brightness and focus control pots, so I settled on using 1 megohm controls instead. R8 and R9 correct the circuit for this difference. You can see that each pot has a current of 200 microamps flowing through them. With 1 megohm, we get a 200 volt drop across each pot instead of the original 300 volts I designed for. These pots now have an operating range around their center position of plus and minus 100 volts. This is still more than enough control range for the D3/130 GH CRT. Take note that the 1 milliamp or 1000 microamp current is split into two paths, one with 200 microamps and the second with 800 microamps. This second current crosses R9, gains 50 volts, and is split into four new paths up through the pots. Each of these paths is 200 microamps each. After passing up through the pots, the four currents recombine into another 800 microamp flow, crosses R8, gaining another 50 volts, and rejoins the 200 microamps coming up through R1. They are now combined into 1000 microamps, our original 1 milliamp, again. This point is sitting at 1220 volts and needs to be buffered before returning to the power supply, which is providing 1520 volts. More on why that is in a moment. Looking at the two pairs of ganged pots that make up the positioning controls, each pair is wired such that when one is increasing its output voltage, its twin is lowering its output voltage the same amount. So one deflection plate becomes more positive and the other more negative. This maintains the requirement that their nominal DC voltage be the same as the voltage of anode 2 to prevent defocusing the electron beam. This form of beam distortion is called astigmatism. You may have seen some oscilloscopes which include a control by the same name. In some cases, the deflection voltage can be so great that it still defocuses the beam and correction may be required. This system's voltages are too small to need that by design. Last, there is a 470K resistor in series with the wiper of each positioning pot. At the other end of these resistors, they are joined by the AC coupled deflection signals before going to each deflection plate in the tube. This is called a voltage summing node. We are adding the DC positioning voltage with the AC deflection voltage to steer the beam where we want it on the face of the tube. We will cover this more in the deflection amplifier episode of the series. We will also be adding a video driver circuit to G1 at that time. Let's move on to the power supply. Does it look familiar? It is 88% the same as the power supply used in the NBTV CRT televisor. The AC input, the transformer, and the two lower voltage outputs are identical to that. The original circuit used a voltage doubler for providing about 760 volts for the James Millen 090901 oscilloscope module used in that project. This project's tube requires a much higher voltage, so I chose a standard Cockcroft-Walton voltage quadrupler. You can see that the power transformer is labeled as providing a 250 volt AC output to our multiplier circuit. But Labguy 4 times 250 volts is not 1520 volts as indicated on this drawing. Au contraire. First, understand that our transformer, though labeled 250 volts center tapped, is not necessarily so. Plus physics and math. Oh dear. It's not so bad. Watch. First, the 250 volts is specified when the transformer is fully loaded to its 25 milliamp output rating. These circuits do not load the transformer that much. So the 250 volt output is actually closer to 270 volts. AC, RMS, sine wave. So we correct by the square root of 2. 1.414 times the RMS value to get the peak-to-peak value of the voltage. Square root of 2 times 270 volts is just under 382 volts. Times 4 is 1,527 and change. Looking at the voltage divider again, we see that the top voltage there is 1,220 volts. The power supply is 307 volts higher than that. We need to drop that voltage. We know our current is 1 milliamp or 1 volt per k ohm of resistance. So we need a series resistor of about 300 k ohms. I used a 360K resistor as that was the closest one I had on hand, and it worked like a charm. All voltages were within less than 5%, and the tube worked perfectly. So here is the boboscope operating and producing a spot. Pretty neat, huh? The positioning controls have enough range to move the spot entirely off the screen in all 4 cardinal directions: up, down, left, and right. In the next video, we will go into the deflection amplifiers and see this scope in action. So that was the deep dive into the boboscope project. Soon we will go back and revisit the NBTV dissector cam project so that you can see where that is at. I'm dealing with some issues with it. It works, sort of, and makes pictures, sort of, and it has led to some improvements in the original NBTV CRT televisor circuit, which I'll get into in a video about that. So I have 2 or 3 subjects in mind to address, and I will get to those as we go, and hopefully we'll get on with the boboscope project and the others. I mean, there's so much to do. I have 1,000 ideas and not enough years left in my life to cover them. So hopefully we'll start putting out videos again on a regular basis. And with that, I'll bid you adieu, and we'll go out with a nice slideshow of the boboscope as it evolved. And until next time, Labguy out.